Hello. Hello, everyone. I'm eating cheese. So are the dogs. They get cheese snackies. I'll wait about one more minute and then I'll get started. Morning. No more cheese. No more cheese, puppos. No more cheese, Hazel. No more. No more cheese. Okay. Let's go ahead and get started. So, I gotta focus this. So not focused. Come on. Focus. It's interesting. If I put something like a calculator into the frame, I think because the calculator has all these little fine details on it that it focuses more easily. If I just have a white sheet of paper, it doesn't even know what's focused and what's not focused. Kind of interesting. Okay. This week we're going to have, I think, one assignment, just today's assignment. On Thursday, I'm going to go over the internal assessment. All right. So let's go ahead and get started. So we're beginning a new topic, and that topic is thermal physics. So this is the part of the IB class where we start to jump around to different topics, okay? The main topic in IB physics is mechanics, which is forces and energy and momentum and kinematics and that sort of thing. And so we've kind of had an introduction to that, so now we're going to jump around to some different topics and kind of get overviews of them. So the first topic is after uncertainties, is thermal physics. Okay. So so what I want to talk about is if you have a sample, so let's say you have a material. Okay, I'm just going to say that this material is shaped into a cube. And if you were to zoom in a whole lot and just zoom in at any part of that and to blow that section up, you would see a bunch of atoms / molecules, okay? So, a molecule is multiple atoms bound together. So you are going to see atoms / molecules. All right. And those atoms and molecules are interacting with each other. Okay, and so this is happening at the microscopic level. Okay, it's happening at the microscopic level. So this block could look to our human eyes as just being completely still, but if we were to be able to zoom in and look at the individual atoms, those individual atoms are actually jiggling in place. They're interacting with each other, and there's a lot going on. Okay, it's just that from our perspective, it doesn't look like there's a lot going on. So because there's all this stuff going on that we can't really see with our eyes, we can only see it if we zoom in. It is called, the energy associated with this is called internal energy. Which is typically denoted by U. Okay. And so internal energy is the energy of, and so when I say energy, I mean it's the kinetic and the potential energy of random microscopic atomic motions. Okay, so it's basically what we think of as heat. Okay, but there is a difference between internal energy and heat. Sometimes I will slip up and I will call this thermal energy. IB uses the term internal energy. I think that I learned it as thermal energy, so it's kind of what I have stuck in my head. But so it's the kinetic and potential energy of random microscopic motions. So this is a real form of energy. It's just sort of invisible because we don't see atoms vibrating randomly. We don't have the vision to see that. But it is there. It is a real thing. And so sometimes we can harness that energy. Sometimes, and one thing I want to say is if you took, let's say I took this sample and I threw it across the room, that does not necessarily add to its internal energy. So even though I'm adding to the kinetic energy of all the molecules, okay, by throwing this thing across the room, by throwing something across the room, you have every molecule all at once moving together. That's not random. Okay, that's a collective motion, so that wouldn't count as internal energy. So kind of the kinetic energy that we've learned about before is a bulk collective kinetic energy of all the molecules together. But when we talk about internal energy, it's the extra energy due to just random jiggling. So important point, it's random. Of course, it's measured in joules, okay, because it's a form of energy. Then there is something called heat, which is denoted by Q. And heat is a transfer of internal energy. Okay. So if you have, let's say you have something that has a lot of internal energy and something that doesn't have a lot of internal energy, and you put them together, internal energy will flow from one to the other. Okay? And that flow of internal energy, the amount that flows, is called heat. Okay? So you could think about heat as a lot like work. So work is a transfer of mechanical energy. Okay. So, adding to the kinetic energy or the gravitational potential or the elastic potential energy, that is work. But if you add to the internal energy by making the atoms jiggle more, that is heat. Okay? So work adds to mechanical energy, heat adds to internal energy. Okay? When you are, so you never say that something, don't say that something has heat. Okay? What it has is internal energy. Okay? You never say something has heat. You say it has internal energy. You can say that it has heat transferred to it. Okay? But do not say that something has heat. It has internal energy, and it has heat transferred into it. Okay. So then there is something called temperature, which is denoted by capital T. And temperature is a measure of the random kinetic energy of atomic motions. Okay. So is there a difference between internal energy and temperature? Yes. Okay. Internal energy includes kinetic and potential energy of random atomic motions, whereas temperature only includes the kinetic energy part of that. Okay? All right? So temperature is measuring the random kinetic energy only. The units of temperature are Kelvin, okay, or degrees Celsius. Keep in mind that Kelvin is not a degree, so you don't say degrees Kelvin, you just say Kelvin. All right. Now, the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15. Okay. So I'm going to stick pretty much entirely to the Kelvin scale. All right. But yeah, so 0 degrees, 273.15. I'm going to stick pretty much entirely to Kelvin, but 0 degrees Celsius is not 0 Kelvin. Okay, negative 273.15 degrees Celsius is 0 Kelvin. All right. So 0 Kelvin means atomic motion is minimized. Okay? 0 Kelvin means atomic motion is minimized. Does it mean that the atomic motion goes away? No. It turns out that because of a more advanced area of physics called quantum mechanics. Even if you are at 0 Kelvin, you cannot eliminate, because of quantum mechanics, you can never completely eliminate the jiggling of the atoms, okay? You've just minimized the jiggling. So there you've got the smallest amount of jiggling possible at 0 Kelvin, okay? Now you might ask, well, I'll box that in too. You might ask, well, temperature is measuring random kinetic energy. Why don't we just measure temperature? Oh, another thing I meant to say is average. It's the average random kinetic energy. Okay. So some atoms or molecules are going to have more than the average. Some are going to have less. All right. So it doesn't mean that every atom has the same amount of jiggling. Some might have more than others. But it's talking about the average. Now you might ask the question, well, if temperature is a measure of random kinetic energy, why don't we just measure temperature in joules? And the answer is you can actually measure temperature in joules. All right. And actually, many of the more advanced thermodynamics textbooks that I have, they don't even use Kelvin. They just use joules to measure temperature. All right. But we're going to use Kelvin. Kelvin is used pretty much unless you're talking about sort of the theoretical aspects of thermal physics. Okay. So these are just some introductory vocabulary terms. All right. So when heat, and remember, heat is energy of random atomic motions. Okay, is added to a sample. Okay, when heat is added to a sample, its temperature will increase. This is assuming, and we're going to talk more about this later on, but this is, there's a question in the chat. Is 0 Kelvin absolute zero? Yes. 0 Kelvin is absolute zero. When heat is added to a sample, its temperature, in most cases, will increase, okay? However, if you have a phase change happening, so if you have liquid turning into a gas or solid turning into a liquid, then the temperature won't change. So for this first lesson, we are going to assume no phase change. So we don't have any transitions between states of matter, okay? Because if you have a pot of boiling water and you add heat to it, it doesn't raise the temperature of the boiling water, okay? What that energy is being used for is to turn more of the water into steam, okay? But the temperature doesn't change. So if you don't have a phase change happening, then you add heat, the temperature will increase, okay? And so there's an equation that describes how much the temperature will increase, and it's the following. Q equals mc delta T. So this is our main equation for today. So Q is the heat added to the sample. M is the mass of the sample. So how much of an effect adding heat to a sample, how much effect that heat is going to have on the sample depends on its mass, okay? If you think about adding heat to the ocean, you know, the ocean has so much mass that it's not really affected by heat. You know, its temperature doesn't change as much in response to heat as, for example, a little tiny droplet of water would. Okay. So yeah, depends on the amount of mass. Delta T is the change in temperature. Okay. So you can see that these are on opposite sides of the equation. So the more heat you add, the larger the change in temperature. All right. And C is called the specific heat capacity. And the specific heat capacity depends on the material. So different materials have different specific heat capacities. So it's a property of the material. Okay. Water has a certain specific heat capacity. Iron has a certain specific heat capacity. Copper has a certain specific heat capacity, etc. So it's a property of the material that you're adding the heat to. Okay. And, okay. So I'm going to flip the page over. So, what is the interpretation of C? Well, okay. So if we take Q equals mc delta T, what if we set m equals 1 and we set delta, so m equals 1 kilogram and delta T equals 1 Kelvin. So if we do that, because m equals 1 and delta T equals 1, we get Q equals C. So what that means is that C is equal to the heat required to raise the temperature of a 1 kilogram sample by 1 Kelvin. Okay? That's the meaning of the specific heat capacity. It's how much heat is required to raise the temperature by 1 Kelvin. Okay? So what does it mean if something has a large specific heat capacity? It means that it takes a lot of heat, a lot of energy to raise its temperature. Okay? So large specific heat capacity means difficult to change the temperature. Okay? So things with a large specific heat capacity, their temperature stays more constant than things that don't have a large specific heat capacity. All right? So by the way, the units of specific heat capacity are joules per kilogram per Kelvin. All right. Just about the largest specific heat capacity around is that of water. So water, and this is why water is used as a coolant, okay, because it's difficult to change the temperature of the water. So in order to cool something, it has to pull heat out of the object. And when it pulls heat out, it's absorbing heat. But so in order to pull the heat out, its temperature has to be lower than the thing it's supposed to cool. And so because water, it's difficult to change its temperature, cold water will stay cold and pull lots and lots of heat from an object that you're trying to cool, okay? The specific heat capacity of water is around 4,200 joules per kilogram Kelvin. And it's just about the largest specific heat capacity. So water is a really good coolant. All right. If you want to get a higher specific heat capacity, you have to use exotic stuff that might be toxic to humans and is really expensive and blah, blah, blah. Okay. So water is really good. Metals. Typically have, metals have a much lower specific heat capacity. All right. Typically around a couple hundred joules per kilogram per Kelvin. All right. So it's like 1/8 the heat capacity of water. So that means that metals change their temperature much more rapidly. Have you ever touched a piece of metal that's been sitting outside overnight? It feels very cold. The reason it feels very cold is because its temperature cooled down a lot more quickly. And then you hold on to the piece of metal and it warms up to the temperature of your hand very quickly. So it's just very easy to change the temperature of metals, whereas water, it changes its temperature much more slowly, okay? I want to talk about a common you very oftentimes see this in on the IB exam. So they take this equation, Q equals mc delta T, and they divide both sides by time. Okay? So what do we have? What is energy per time? Does anyone know? Type it into the chat if you know what energy per time is. Energy per time. Oh, actually, I'm just gonna go forward because for whatever reason my live stream is really lagging behind, it looks like. So energy per time, velocity is distance per time, but energy per time is power, okay? Power equals energy per time. Okay, so we can write this as power equals mc delta T divided by the time. So I like this equation because let's say you have a burner on your stove, for example. Okay, that burner is outputting a certain number of joules of heat per second. Okay, so that burner has a power. All right, and your food has a certain specific heat capacity. It has a certain mass. It has a certain amount that you're trying to raise its temperature. Okay? So, you might need to raise the temperature by 20 Kelvin or something. If you know the power output of your burner, you know the mass, you know the specific heat capacity, you know how much you need to raise the temperature, you can calculate how much time it should cook for. All right, so that's pretty cool. So this equation is used on the IB exam from time to time. All right. Okay. So, the next topic I want to talk about is called calorimetry. All right. So here's the idea behind calorimetry. We have 2 objects, or 3 objects, it doesn't really matter. Okay. Object 1 has a certain, I'll say object A. Object A has a certain initial temperature. Object B has a certain initial temperature. Okay? They are brought into thermal contact. So thermal contact means they are allowed to exchange heat. Okay? All right? And heat is going to flow between these objects. Now, as the heat flows, one object is going to get cooler, the other one's going to get hotter. Okay, the heat flows from hot to cold. So we'll just assume that TA is greater than TB. Some time elapses. And then after a while, they will reach the same final temperature. So there's a final temperature. It is called T sub F, and it's the same final temperature for both of them. And once they reach the same final temperature, there's no more net heat exchange, and so we say that they've reached equilibrium. Okay. Calorimetry says nothing about how long it takes to reach equilibrium, but what calorimetry does is it allows you to calculate what that final temperature will be. Okay? All right? So kind of what happens is if we were to do a graph of temperature versus time, okay? So maybe A starts at this temperature and B starts at this temperature at time 0. Then as time goes on, their temperatures will reach a value that is common to both of them, and that's when they reach equilibrium. Okay? So this is the final temperature. And yes, it's an exponential decay to the final temperature. All right, so what is the fundamental equation? So the heat gained by A plus the heat gained by B has to equal 0. Okay? So if one of them gains 5 joules, the other one lost 5 joules, so they add up to 0. All right? So this is assuming that it is isolated, an isolated system. So an isolated system is one that is not exchanging heat with its surroundings. Okay. So this becomes, if we plug in Q equals MC delta T, we get M sub A times C sub A times T final minus T sub A. So that's the change in temperature because it starts out at temperature T sub A and it ends up at temperature T final, plus M sub B, C sub B, T final, minus T sub B. So this is the change in temperature of object B. And so you can see that they have the same final temperature because they reach equilibrium. And those have to add up to 0. Okay, so this is kind of our master equation for calorimetry, for predicting the final temperature. All right, so let's do an example. Let's suppose that we have a sword of mass we have a sword of mass 4 kilograms, specific heat capacity. Now a sword is made out of metal, so maybe the specific heat capacity is 450 joules per kilogram Kelvin. And it has initial temperature of, let's say, maybe 900 Kelvin. Okay. Is submerged in, let's say, 8 kilograms of water at temperature, let's say the initial temperature is 293 Kelvin. So 293 Kelvin is room temperature in Kelvin. All right. What is the final temperature? All right. What is the final temperature? So we're going to be using this equation here. This is a fairly realistic example. If you are making a knife or a sword or something like that, you have to do what's called quenching it. So quenching metal, or quenching steel in particular, is the process of cooling it down rapidly by dipping it in a liquid. So that liquid could be water or it could be oil. And so, like when I'm making a knife, I'll get the knife up really, really hot, and then I will dip it in some oil, and that cools the knife down rapidly. Okay. And cooling it down rapidly basically makes the steel crystallize. Okay. And the crystalline steel is very hard. So that's what allows the knife to become structurally strong, structurally rigid. It's a little bit of a trade-off. So the faster you cool it down, the harder the blade will be. But there's a trade-off between hardness and brittleness. So actually, when I was making this knife, I cooled it down too rapidly, and it became the blade became extremely hard. It's a really the steel is very hard, so it can hold its sharp edge very long. But I made it a little bit too brittle, and the tip broke off. So I actually intended for this knife to be more like this long, but when I quenched it, it's called quenching, this process of cooling it very rapidly, the tip just went and broke off because it became so brittle that literally just setting it down after I quenched it, the shock from setting it down, the tip just went and broke off. So that was a bummer. So yeah, that's called the quench. And it's really cool because you can feel the bucket of oil, and dipping something that is 900 Kelvin into a bucket of oil, even if it's something only this big, will make the oil like piping hot. It's just really cool to, or neat, I should say, to dip something into a bucket of oil and have that thing be so hot that you dipped into the oil that after you've dipped it in, the oil itself is too hot to touch. So it's pretty cool. Pretty neat. All right, so let's solve this problem. So we have our equation, which is MACA T final minus TA plus MBCB T final minus TB. That's equals 0. Okay. So let's let A represent the sword. Okay. So the mass of the sword was 4 kilograms. It was made out of a metal that has a specific heat capacity of 450. The final temperature is unknown, so I leave that as a variable. The initial temperature is 900 Kelvin. Okay. B is representing the water that we're submerging the sword in to quench it. And that the mass of the water is 8 kilograms. The specific heat capacity of water is 4,200 times T final minus the initial temperature is 293. And that equals 0. So this is an equation that we solve for T final. All right. I'm going to so I'm going to share a window here, and I'm going to go to a website called Wolfram Alpha. My computer is going really slowly because I'm live streaming simultaneously. But if you don't want to spend the time, so we have this equation here, you can do the algebra. But if you don't want to waste the time solving the algebraic equation, I would recommend going to Wolfram Alpha and just typing in your equation. So my equation was 4 times 450 times T final. So I'm just going to call T final X minus 900 plus 8 times 4,200 times X minus 293 equals 0. And Wolfram Alpha just solves things for you, makes it pretty easy. So it solves it, and it says the solution is this. I just want the approximate form. So the final temperature is 323.9 Kelvin. All right. So that's the final temperature. So you can see why water is such a good coolant, because you have something that was really hot. All right. And if you think about the hot thing, its temperature dropped almost 600 Kelvin. The water's temperature went up only about 30 Kelvin. You see what I'm saying? So the water's temperature hardly changed at all in response to having something extremely hot dipped into it. Now you can feel that temperature difference, okay? But it's not a gigantic temperature difference like going from 900 to 320 Kelvin is, okay? Another thing I could ask you is how much heat is exchanged? Okay, so to figure out how much heat is exchanged, all you need to do is take one of the two. Okay, so let's take the sword, for example, and I'm going to do Q equals mc delta T for the sword. Okay, the mass of the sword is 4. Its specific heat capacity is 450. Okay. And then the change in temperature, well, it ends up at 323.9 Kelvin, and it started out at 900. Okay. So I can work that out, which I will do. 4 times 450 times 323.9 minus 900. And I get an answer of pretty much exactly minus 1 million joules. Okay, now why is it negative? It's because the metal, its temperature dropped, so it actually lost, it gave up heat. All right. If we had done this for the water, we would get Q equals plus 1 million joules, because the heat that was lost by the metal was gained by the water. So it doesn't matter which of the two objects you choose to do your calculation. You take your final temperature and you do mc delta T for one of them. Okay, and that'll tell you how much heat was exchanged. So I usually like my answers to just be positive numbers. So you would, whichever one was positive, you would just state that as your answer. So they exchanged 1 million joules between them of heat. All right. So this equation right here is really the statement of conservation of energy. Okay, it's saying that if one thing gains, it's saying that heat is a form of energy. Okay, if one thing gains heat, then the other thing must lose heat. All right, but this is assuming an isolated system. Okay, so I want to talk about just very briefly a couple of twists that we can have on this basic equation here. If you have more than two objects, then what you have is Q1 plus Q2 plus Q3 plus dot 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 equals 0. So however many objects you have, the total amount of heat gained by that system has to be 0. Okay, so I think there's a problem on the homework with 3 items. All right, and that's just conservation of energy. Okay, the heat is moving around between them, and there's no heat coming in from outside. There's no energy coming in from outside, so the total amount has to stay the same. What if you have a system that is not isolated from the surroundings? Okay. If you have something that is not isolated from the surroundings, then the surroundings are going to input heat into the system. Okay, so in this case, Q1 plus Q2 will not equal 0. Q1 plus Q2 will equal the heat added from the outside. Okay, so it's just the heat added from the outside. So you have homework problems that deal with each of these two cases. But if it's an isolated system and there's only 2 objects, then you're just using this equation right here. All right, class, that's my lesson for today, and I will see you in the Zoom room.